Recording. Chapter 14. Machine does two things. It prepares and sends out a signal, and then it listens. And then takes what it hears and manipulates that data. On 216, I'm not going to read through this, but there's a transducer. There's a pulsar, a beamformer, a receiver. The receiver has a number of functions to it. A display, of course, that's what we look at. Storage, very short-term storage, like your CineLoop. Long-term storage, like you saved your image. And a master synchronizer, which interestingly enough, doesn't really show. Oh, wait, I have a note here. I totally missed this note. Yes. Okay. Master synchronizer is going to go by another name. A much simpler name. So, yes, we do talk about the master synchronizer as well. So, pulsar. Pulsar. I feel like we already talked about this a little bit. Maybe no, I don't know. I feel like I already talked about this. Pulsar. You have direct control over the pulsar. When you control the power button, that on our machine, the far right-hand corner, power, the pulsar determines how much power each pulse has. And so, let's just, we have our power button. And Edelman, for the reasons of bioeffects, I'm just saying this now because one of my students who actually went to the Edelman seminar said that he really emphasized the difference between using power and gain, and that according to him, you always reduce your power to the minimal amount usable for the exam. And in certain cases, when the screen is too bright, just turn your power down rather than your gain. For the purposes of bioeffects, that's an understandable position. Always use less power than you need. Realistically, I don't touch the power button. It's all about gain because I personally want my power up high all the time. It produces a better image. End of story. So we already struggle enough in ultrasound. Why make it harder? But according to bioeffects and according to possible questions on the SPI, if you have a choice, if you have an equal choice between power and gain and reducing something, reduce the power on the SPI. In the real world, do what you want. Because these powers are not very, we're not blowing up anything. So, during transmission, transducer output. You could reduce the output to near zero. You could increase it to like 100 volts. That's a lot. You don't want to, by the way, if a transducer is old and the wires are exposed, you go to your boss and say, I'm sorry, I'm holding 100 volts of unshielded wire in my hand. That is dangerous. And unless you want to get sued, let's get this fixed. So you shouldn't use transducers that with frayed wires. I'd be afraid to use it. All right. Okay. So I kind of already alluded to this. So the thing about power, is it signal to noise or noise to signal? Signal to noise. I know. All right, let's put signal to noise ratio. When you're dealing with noise on the screen, and we're almost always dealing with some amount of noise, it's usually some kind of artifact. And if you reduce your power, you end up reducing the strength of the echo. So now you have weaker echoes and artifact at the same time. It's harder to deal with. If you increase your power, you increase the strength of your echoes, the real information. And the noise is still there, but it's less noticeable because you have more power going into the actual useful information. Now, some artifacts will be increased too, but we're really talking more about noise, just certainly electronic noise certainly would be better off. Other things that we can call the power output gain, which is a no-no, don't call it that. Acoustic power, pulsar power, energy output, just power in general. We don't want to use the term gain. Gain is something that happens gain is listening. You turn up your gain, you're not turning up the power, you're turning up your listening. You're getting your ear closer in a sense. Or you're cupping your ear with your hand to hear better. That's gain. So don't ever use gain for power. And in fact, you'll never see it written like that. So it's just power is power. Well, we could skip thermal index, mechanical index, because we talked about that in chapter 24. Adjustable, yes. So you have direct control of the power button. It does have a preset, but you can always turn it down or perhaps even up. It's lower power, lower bioeffects, higher power, more chance for higher bioeffects. All right, I mentioned the signal to noise. Oh, yeah, okay. So signal to noise ratio. If I raise my power, the signal to noise ratio is better. Now, we don't have we're not calculating signal to noise ratio, but it just knows that it's better because my signal has increased, but my noise has stayed the same. So signal being the good stuff, noise being stuff we don't want to hear. So we increase the noise, that's better. Oh, I was just about ready to tell you about something that is actually from chapter 15. Oh, okay, never mind. No. So I just had a question about scale and power. Nope. You're here, let me come off to the side. Remember, your scale can be any number of well, a few things. One scale is your color scale with you know, with red, blue, like that. Your color scale refers to, in this case, I put 30 centimeters per second. That's controlled by our PRF, the pulse repetition frequency. Same thing with the that also is a scale. This is like a pulse wave. And once again, we change that with PRF. So yeah, those are different things. The power, actually, let's see if I can. If I were to show graphically or kind of give an idea of what power might look like, the electrons, in other words, the voltage, they're traveling from the pulsar to the beamformer here. I can decide to use fairly low power, or I could decide to turn the power up and create higher power. So that the light green represents a higher voltage. What I did is I did my best to keep the frequency of voltage the same. I've just increased the power of it. The other thing the pulsar and pulsar does. Okay. Let me just see what your question was. We use the word scale. Okay. Totally understandable. Now I get. Okay. The second thing the pulsar does is kind of time our PRP or the PRF. Either way, it's the same thing, right? Same, two sides of the same coin, PRP, PRF. Which is connected to the scale, which is connected to the power. So that all gets a little confusing. But so this is a separate function. The power is how strong the voltage is. And the PRP, or the PRF as it were, is how many voltages, how many of these are coming from the pulsar to the beamformer per second. So we have direct control over that function as well. And as you recall, when you change your depth, the pulsar is automatically collecting or automatically calculating the best pulse repetition frequency for that depth. In color, now we have direct control of the pulsar through the PRF, the PRF button. So in grayscale, its depth changes that. So let's just go ahead and. That one, the engineers have already figured it out for us. And they say, okay, at 5 centimeters, this is what your PRF is going to be. At 10 centimeters, this is what your PRF is going to be. In color, it obviously starts with a certain PRF, but that function of pulse repetition frequency is Doppler only. You're not changing the grayscale in the background PRF. You're changing the color only, or the spectral only. And that, for kind of complicated reasons, changes our scale. So depth, that's gray, in grayscale, and then also Doppler. And that's actually our PRF button. Okay, so two functions of the pulsar. We have direct control over both of them. Higher power, better image, more bioeffects. So if you are concerned about bioeffects, go ahead, turn your power down and your gain up. If you turn your power down, the whole screen's going to go darker because everything is weaker. That's okay, just listen harder, use your gain. It's safer, but by doing that, you've increased you've decreased the signal to noise ratio, which we actually want to increase that. We want more signal than noise. And when you drop your power, you start to get more noise than signal at some point. So higher power is better for imaging, worse for potentially the body. 2 times where I would think it'd be important is first trimester babies. And if you're going to scan right through the eye, if you're going to do a transcranial Doppler and go through the eyeball as one of your windows, you definitely want to have low power then. So pulse repetition period. All right. So then we get to the beam former. Remember all this stuff? Well, we had to learn about steering and focusing and apodization. All of that happens in the beam former. And so we'll just draw some arcs in. Like if we send this electricity down to the beam former, this voltage to the beam former, one pulse of voltage goes to the beam former, and then the beam former, as the voltages, as these electrons are traveling in this direction, this is decided that we're going to steer the beam, I don't know, one direction or the other. Let's say it's steering to the right, because this electron is going to reach the transducer sooner than that electron down here. Also, we can focus with the beam former. So all of these pictures that we're showing, that we were looking at back in chapter 12, that all happens in the beam former. That's controlled by the beam former. So these outside electrons are first, the inside are last, and that's how they're going to meet the transducer elements. These elements on the outside are going to be stimulated first. The elements on the inside will be stimulated last. That creates a focus. And of course, we could also steer and focus our electrons, and that goes all the way down to the transducer. And the last thing, apodization. That was, remember we have to deal with, we have a main beam, but then we like to imagine that there's only a main beam, this little laser beam of sound, but no, there's weaker beams going off to the side. And in the case of a multi-element transducer, they're called grating lobes. Well, how do we deal with grating lobes? Well, one of the 2 methods of dealing with grating lobes is to have, let's see, kind of weak electrons out on the side here, but then strong electron, a weak voltage, I should say, weak voltages on the side, strong voltage in the middle. Most of that excess beam, those grating lobes, are created by the outside elements, so we weaken those. That also occurs in the beam former. Whoops. Instead of hitting Control Z several times, I hit Control S, and I made my computer angry. Okay, so let's just look at this real quick. Did I get everything? Steering, focus. Oh, right. apodization, but I forgot dynamic receive focusing. So the electrons coming back, ooh, this is good, this is good. Remember when I showed, you have like a little object in here and it might be hit with a pretty strong or straight beam of sound, but the reflection does that. Remember that? So the reflection, even though this, oh, let's actually make this green. This is like a flat surface. So even though it was a flat surface, it has a curved echo. That's just how sound works. It kind of, as it's leaving the source, and when I say source, I mean the reflector, as it's leaving, it spreads out, and it spreads out, it creates a curved. And so it's coming back, let's see, curved through the wires in a sense it's curved. It's actually, when it actually hits the beamformer, now we're going in this direction, electron, electron. And then the beamformer says, no. I know how echoes are formed. I don't think that this is a curved surface. I think that I'm going to put a delay in the middle. So we'll delay, we're going to allow these electrons to catch up with the middle. And so it ends out creating an echo pattern that reflects the flat surface that it actually was. That's dynamic receive focus. And of course, dynamic aperture. Typically, I'm using the entire beamformer to create a image. That must mean, if I'm using the entire beamformer, so far I've been talking about a phased, I get these confused too. Linear phased array where every element's used every time. But let's say this isn't a linear phase, it's a linear sequenced. Now I have maybe a beam coming out of only these wires. Because we're going this direction now. Dynamic aperture on the way in. So dynamic aperture focus can mean that on one pulse, I use this many, but on the second pulse, maybe I use that many channels or elements to create my pulse. And then maybe on the third pulse, if I have a, maybe I'll use that many. These are all electrons and they're all traveling in this direction, eventually making its way to the transducer. So you could see, hopefully, that I'm changing the aperture by using more or less channels. Each one of these wires is a channel. Same thing on the dynamic aperture on the receive. So dynamic aperture receiving, as time passes, I might use that many channels to listen. And then time goes on a little more. I might use that many channels to listen. Goes on even farther. I'll use that many channels to listen. So I know this is all inside of the electronics of the beamformer, but this is equivalent to the transducer changing its aperture in both sending and receiving. So dynamic receive aperture, dynamic aperture in general. Also called a digital beam former. Okay, so the transmit receive switch, page 222 I'm on, that is a fancier name for it is the master synchronizer. I'm going to write that in. I had forgotten because I had to look it up because I'm like, not this year, but in past years I've had to look this up. Like, what is the master synchronizer? And finally I found somewhere where it actually said it's your switch, your TR switch. So it's also called a master synchronizer. Ooh. All right. TR is a little bit easier. Transmit, receive, switch. In other words, when the machine is in transmit mode for a microsecond, couple microseconds, this switch is making sure that all the voltage created back here in the beam former, so my little electrons are moving along, going in this direction, going through here, and the transmit receive switch says, okay, yeah, we're in transmit mode right now. And that's, of course, is going to send everything all the way down to the transducer and create a sound wave. Now, like we said, no, did we say? Yeah, we did say. That could be upwards of 100 volts. A 100 volts is a lot of energy in your hand, not so much in the sound beam, but in your hand, 100 volts is a lot. You don't necessarily want to touch that. Then the echoes come back. And then those echoes create electrons because it's a piezoelectric element. They come back. And from there, the TR switch is now spends 99% of its time because it's listening 99% of the time. It spends 99% of the time in receive. And it's going to send electrons down to the receiver, appropriately named. Now, this is so important because the difference in voltage between 100 volts going out and millivolts coming back is huge. If this switch did not work correctly and the original beams 100 volt voltage was coming out of the beam former, and if it went down there, poof, whole bunch of smoke would come out of your machine because you would fry the entire receiver. The receiver is designed to deal with millivolts, not hundreds of volts. So that's the biggest thing it does. And it's an incredible timing device, really. In fact, I'm going to put a little stopwatch here. It looks like an old-fashioned alarm clock, but it's a stopwatch. It has to time everything perfectly, synchronize the time. Okay, now in the book they mentioned channel, and I've already mentioned it a little bit, but let's talk about that a little more carefully. The channel, here, let's, I didn't make anything big enough here, but we'll put a couple of lines in there. All right. A channel is one element. Here, let's give myself a little more room. Let's just choose, I'll make an element right here. An element and the wire the one individual wire that runs from that element all the way back to the receiver is a single channel. So a channel is made up of a single element and the electronics in the beamformer, pulsar, and the wire that connects them. So I guess we could also say the wire here, and let's see, I use the last element, so we'll say that wire there. So even though there's a switch here where the wire is going in two different directions at the TR switch, it's all still considered one channel. So if you think about it, you could destroy a channel by, you could drop the transducer and break one element, and that whole channel is useless. Or you go back in the beamformer and you break that, the wire, the electronics back there in the beamformer, then you've effectively broken the element as well, or at least that element is no longer useful because it's no longer getting a charge from the beamformer, and it's no longer sending information back to the receiver. Receiver. This is where a lot of things happen. Amplification. There's a baseline amplification that automatically occurs. We have control of the amplification because each CW, wait, no, PW, no, that's pulse wave waving? Color, 2D, I can't remember what they all say, but we want to turn up our color amplification. Yes. I scared myself for a second. Amplification is the same as saying, well, we're going to talk about it, gain. We're going to talk more about these, each one. Compression is it's a form of taking vastly different numbers and compressing them together in something that's a little more palatable. It's like taking a gigantic sandwich you can't possibly fit in your mouth around, and you shove it all together, and then you take a bite. Compensation. That's actually time gain compensation. So you guys know about that. Demodulation, that's electronic thing, and then reject. And we kind of have an idea about reject as well. So let's talk about these. Amplification is our gain. Everything on the screen is amplified. There's a basic amplification. The millivolts that are coming back are really, really weak. And so there has to be an amplifier just to make them usable. So they have to go through an amplifier first, just so you could actually see and use the voltages that are coming back representing the echoes. So that's gain. That's the whole screen. There's an automatic amount of gain, and then there's also amount of tech control as well. So if it's too dark, you turn up the whole screen's gain. You amplify the whole screen. It's in decibels. Oh, this is interesting. So typical amplification is 60, and I mentioned they have to amplify a lot, to 100 decibels. Remember, decibels are logarithm. Why do we use logarithm? Because the numbers are huge, and it's just easier for people, not for me, but for some people apparently, to understand. That's basically the same as saying $1 million to 100 million decibels. No, not times. So they're gaining the whole system by 1 million to 100 million times the actual voltage. So that's a huge amount. That's why that TR switch is so important. This amplifier, or this amplifier, if it received if it received 100 volts and then tried to raise that by 1 million to make 100 million volts, that would not be good. So we don't generally want that to happen. Preamplification. Missed this almost. Preamplification in the transducer itself. So not all transducers have that, which is why I did the question mark here. But sometimes the signal coming back from the body is so weak that the electrons can't even make it. They're like, ah, and they die. They die halfway up the cord. So sometimes there's even a small preamplifier inside of the transducer just to get the voltage all the way back to the receiver, which then further amplifies it. Like I said, these echoes are millions of times weaker than the original sound beam. So just remember, when you turn up your amplifier, when you turn up your gain, everything is turned up, good and bad. And ugly. And so like if you have some ugly stuff inside of your blood vessel that's not real, it's not exactly noise, because noise is just noise, but it's an artifact. It's a misplacement of it's a real echo in the wrong place. That's what most of our artifacts are, or many of our artifacts are. When you turn up your gain, you turn up those as well. So good and bad gets turned up when you turn the gain. Compensation, you guys know what that is. That is actually your time gain compensation. Now we know every center, well, it depends on your frequency, but you could lose in your beam itself, you could lose half of the energy of the beam every centimeter, maybe every 2 centimeters, depending on your frequency. Half the energy. So you go a centimeter, let's say 1.5 centimeters. You go 1.5 centimeters, and your beam is half as strong as it was when it started. You go another inch, 1.5 centimeters, and your beam is reduced by yet again in half, and then again in half, and then again in half. Well, obviously means your echoes are going to be weaker and weaker the farther they have to come. And those echoes, it's a double whammy. Not only are they weaker because the beam is weaker, but now they have to travel farther. So it's a total double whammy. There's a built-in compensation. If we could see the compensation curve, it would look, well, like this, where the gain is relatively small. Relatively, as like maybe it's 1 million times of gain, 1 million, 60 decibels of gain, versus down here where you have a large gain, because you need that gain. And so there's a built-in, because the engineers understand that no matter what you're scanning, there's always going to be a huge amount of loss of power as the deeper you go. But then we have control of this curve with our time gain compensation. Also in decibels. Yeah. So this is kind of it's a tricky concept. So let's think about this. Well, let me just draw this out again. I'll just draw an ultra. Here it's a linear transducer, and we're going pretty deep. And we have these little. And let's just say we go to 10 centimeters here. As the beam is coming down, yeah, I'll draw a beam coming down, and no, that's not gonna work. Well, anyway, the attenuation is significant. Let's say it's let's say it's 3 decibels here. That's the same as saying half strength. Now let's see, that would be 6 decibels about here at number 4, 6 decibels there. So that's half of the half. So I guess we could say it's quarter strength. And let's see, another 5, 6, 7, 8. 9 decibels by the time you get here. So now we're at 1/8 strength of the original beam. And so the engineers automatically build a gain system that's a time gain, because, oh, let's see, 13, 26, this is in microseconds. You could look at it as depth, right? But it's also in time, because this is a timing machine. All the way down to 130 microseconds here. So let's see, like 130, let's just say 70, let's just say 70 microseconds here. Okay. So when the engineers said, okay, at 13 microseconds, we're going to gain it 50 decibels. At 26 microseconds, just 1 centimeter later, we're going to gain it at 65 decibels. We go down farther at 70 microseconds, we're going to gain it at, I don't know, 75 decibels. And so it's saying it knows that for every microsecond that goes by, it has to give more gain to the system. That's the built-in gain. And then we come in and say, nope. And we on our stupid machine where you have to actually find the TGC button. That's the only machine I've ever had that. On page 226, there's a TGC board that's a little more common. And so that says, no, instead of saying, I'm going to gain it, what did I say, 75 decibels here? I say, you know what? No, my image is too dark at 5 centimeters. So I'm going to move that toggle over, and I'm going to make this at 5 centimeters. I've moved my gain over. So at 5 centimeters, it's now going to gain it at, oh, I don't know, let's say we're going to cross out 75 and make it 85 decibels. Now I'm happy with my picture and we can move on. Hopefully that makes sense. Time gain compensation, depth gain compensation. Time and depth are really synonymous. They're the same thing. Time and depth, same difference. And swept gain because you kind of sweep them to the side. Page 228. I don't usually touch this because it's just so stupid. But I think I better, because if it's on the machine, if it's on the test and I don't cover it, I'd feel very guilty about that. So let me just go ahead and build a gain. So it's gonna go like this, like that, and like that. Okay. Page 228, if you want to follow along on that. Anatomy of a TGC curve. At superficial depths, reflection undergo very small amount of attenuation, so there's a small amount of gain. In the region of the slope, and so that's, I don't know why this is called a delay. But the delay is where the compensation curve begins. So they don't really curve it right from the start. They have in the near gain, they don't curve, and then they start curving it soon after, probably around 1 centimeter. It's called the slope. Or slop. For some reason, at the depth of the knee, reflections are maximally compensated by the ultrasound system. In other words, there is no more gaining left in the system. So that's considered the knee. And then we have far field, right? Far gain. I don't know why we care about this, but I don't know why we care about the delay, the slope, the knee, and all that. All we really need to know is what I've already told you about. It's a delay. Every microsecond that goes by, you're gaining the system more. Compression. You guys know compression. You just don't know you know compression. Dynamic range. So once again, there is a certain amount of compression that we don't have control over. It's like there's a minimal amount that has to occur. And so there's a built-in dynamic range or a built-in compression. And then there's our ability to adjust it as well. So the first compression, and there's a number of them. So the first compression keeps the electrical signal levels within the accuracy range of the system's electronics. What does that mean? Well, if you have signals coming back that are many decibels difference, thereby creating many orders of magnitude of a voltage difference between one echo and the next, well, some of those echoes might be a little bit too strong for the electronics, and it'll overwhelm the electronics. And then the others are perhaps so weak that they're going to be ignored. So the first compression is to take, and I always use my dynamic range sponge. It's also my bulk modulus sponge, but today it's my dynamic range sponge. And if you could see, I have perhaps my lowest signals over here on my left hand and the highest signals over here. But when I compress, so I'm shoving this all together, I still have lowest and highest and middle and all of that. It's just that I've put this into a little more of a, well, this is my Dagwood sandwich. I squeeze it all the way down. I can take a bite out of it. And essentially, this is the electronics are saying, okay, now we could deal with this. All right, cool. And then the second compression keeps an image grayscale content with the range of detection of the human eye. Humans can only distinguish between 20 shades of gray, and no, not 50 shades of gray before any of you say it. I could usually figure out who thinks of it first too. Anyways, so you have all these shades of gray on our screen. Well, when you turn your dynamic range way up into the 200s on our decibel range, it gets to the point where the difference between echoes is so slight, there's such a slight shade of gray difference that we can't detect it. So once again, we squeeze it down. The brightest, the most echogenic is still the most echogenic. I think I got it backwards. That's okay. Most echogenic to the most hypoechoic are still on the outside. We've just squeezed it down to something that's a little more palatable for us to be able to see. So this is adjustable. When we do it, it modifies the grayscale mapping. When they say grayscale mapping, they basically say, you can, if I don't compress at all, the map has the, what did I say, most echogenic over here to the most hypoechoic, and there's a map or there's a whole variety of colors in between of shades of gray. And then when I squeeze it down, I'm squeezing down the map, basically. How every voltage coming back to the receiver is interpreted and then put onto the screen is the map. When I personally, my dynamic range, I like a pretty high dynamic range if I'm looking at certain organs. It kind of depends on how well I'm seeing them as well. So if I'm looking at a well-behaved infant, well, you can imagine infants are pretty easy to scan. I actually turn my dynamic range up pretty high because I like to see as many shades of gray as I can. I'll just see all the little details that kind of come out with that. Other people disagree with me. There's a person in town, most notably, who really likes everything more contrasty because he thinks you get better imaging. I disagree, but I'm not going to belabor that point. But When I'm doing certain exams where I don't care about the texture of the tissue, I'm more concerned about, is there blood flow? Is there not blood flow? In that case, I usually turn my dynamic range down because I like to see a little more contrast between the brighter tissue and the darker blood vessels. So that's how I personally use dynamic range. Let's see, I have a note in here, I forgot. Important to note, although increased dynamic range makes a much nicer, more meaningful image, lower dynamic range increases contrast resolution. I'm going to hold off on that because I swear this book gives us two different answers on that. It's more contrasty when you have a lower dynamic range. It doesn't go from bright to less bright to kind of dark to more dark to hypoechoic to anechoic. It kind of goes from bright to anechoic really quick. So there's more contrast. So therefore more contrast resolution. But that's kind of one resolution that I'm not so sure I want. I'll get back to you guys on that. I think I've done research on this a number of times, and people actually have very different ideas on that. Okay, more about compression, weak signals, blah, 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 blah. Demodulation. Okay, you kind of know what demodulation, no, you don't. Well, you might, I don't know about you. We haven't spoken at all about demodulation. This is something that occurs totally in the background. We do not have control over demodulation. But we all are familiar with these. If you have an Apple phone, you're very familiar with this particular item. But I also have, coming from my computer, comes over to this block right here. And what these all have in common is that they change the voltage, so we're not blowing up our machine with 120 volts going into our phone or into our computer. That's one thing it does, but it also, computers, electronics don't deal with alternating current. This is more than the book has given you, but I think it's worthwhile. Just kind of get an idea of what. This is AC. Now, what's running through our walls in our homes is a very controlled alternating current of 60 hertz or thereabout. So basically every back and forth. See, electricity is not quite the same as sound, and so you got to keep that in mind. But every back and forth is an alternating current. Incidentally, your electrons in alternating current, everyone thinks that their electrons are flying through the wires. They're actually not. In alternating current, the electrons are just going back and forth. The electric field is going through at close to light speed, but the electrons themselves are just going back and forth. But we don't need to talk about that right now. All we just need to know is that alternating current is literally a current that goes this way and then that way and then this way and then that way and just keeps going back and forth. That's our normal household current. Electronics can't handle that, or they prefer not. They prefer DC because it's done dirt cheap. And I'm not 100% sure why exactly electronics, computers, phones, ultrasound machines prefer DC, but they do. With DC, the current is going one way, direct current versus alternating current. So all the electrons travel in one direction. The other thing electronics don't like is a lot of variability in the voltage. Electronics really require a smooth voltage. And so the second part of after rectification is to take, and so I'm sorry, rectification then, I kind of jumped up forward a little bit. It takes all the negatives and brings them up to positive electronically. Don't ask me how it works. So you have all these voltages kind of above our baseline, but it just means that they're going in one direction, but it's really, you know, it's like fast pulses, and the machine doesn't necessarily want that. So then it smooths, whoops. It smooths them out to create one smooth, easy to manipulate, easy to use voltage blip of voltage. Not adjustable. This happens in the background. No effect on the image. It's just really, it's just going from regular voltage, AC voltage to DC, and that's basically these steps. I suspect there's a lot more to it, but A, I don't know, and B, I don't care. Does anyone know what a electrical engineer uses as birth control? Anyone? Anyone? Their personality.
That was awful.
And true. All right. Okay, reject. We have control over reject. In grayscale, I'm all for using reject in grayscale. Very low level signals on the display may be associated with either real information or sometimes not so real. The nice thing about reject is that you get rid of the noise. You reject listening to that noise because whether it's noise or not, the machine is still interpreted as something worthwhile putting on the screen, and that might not be worth your while. So you turn the reject up, you just ignore the smallest signals. But as we've spoken about, that is dangerous. Because let's see, let's use the, no, we're gonna make it, there's like no color I could use to show hypoechoic because everything's already white. All right, because as we already know, obviously my vessel isn't black like it should be, anechoic. Just imagine it's anechoic, and imagine that this plaque in here is very, very hypoechoic, but not quite anechoic. So there's like just, you know, you can barely see this in here. Just kind of imagine. And you turn your reject up, and the reject comes along and says, yeah, it's not there. Not there. And then you're like, oh my God, how do I know? Well, that's why we always fill from wall to wall. That's why I tell you guys it's important in the bulb to fill from wall to wall. Let's see, we have a little bit of, just a little bit of reversal of flow right there. If you show this to an attentive doctor, some doctors will not see this, but others will. They'll stop you and they'll say, all right, go back, see this patient again, and I want to see the entire bulb filled, because how do I know that that's not hypoechoic plaque in there? So I am a fan of reject. Don't overuse it. There's actually also a reject on spectral, which I never use. So we're going along with maybe even a little reversal of flow and everything. And sometimes there's important stuff going on down here. I shouldn't fill that in. Okay, good enough. You turn on reject when using pulse wave. I am not a big fan of this. Because now you've potentially erased some important information. So I always have my reject at 0 when dealing with pulse wave, because these little doodads of information can sometimes tell us something. What this is, by the way, can be wall thump. Now, we all have wall thump to a degree. Every time our heart beats and our pulse goes through our arteries, the walls vibrate a little bit. That's fine. But if this wall thump becomes really noticeable, oh, and by the way, our velocity scale, let's say, is 0 to 300, and this is a carotid. So now we have increased velocities plus a significant, let's say a more significant wall thump. The wall thump just kind of, it says, yeah, not only do our velocities are increased, but the wall is actually really getting hit hard with this high velocity of flow. And so that wall thump is important stuff. And if you reject it, it's gone. Gone. I don't like that. Let's see, adjustable, yes. Effect on image, rejects all low-level signals. Oh, it's also called I wrote this in my book. Damn it. Also called a threshold filter, or sometimes just threshold. In other words, sound voltages have to reach a certain threshold in order to be displayed. And if you turn up the threshold, all right, next subject. If you turn up the threshold, it's going to be harder to see. All right. Next subject. Okay, this is tough. Well, not too bad. not too bad, but it's not too easy either. Okay, dynamic frequency tuning. Now we've already dealt with dynamic apertures and dynamic focus and dynamic, dynamic focus. Now we're talking about dynamic frequency tuning, a whole new concept. Okay, so we already know that by creating a transducer with backing material, which shortens the pulse, that pulse is no longer has a high quality single sound to it. It has ugly sound with multiple frequencies. Another way of saying that, it has broad band, also a wide dynamic range. Another way of saying wide dynamic range. And so I've shown here, you know, everything from the red, the highest pulse, to I guess the dark blue is the lowest frequency. I'm sorry, the highest frequency is the blue, and the low frequency is the red. But all of these are inside of this pulse. Many frequencies are produced, and then on a distribution diagram, it shows okay, well maybe the middle is 5 megahertz, and it goes up to 7. There might be some more higher frequencies, but useful goes from 7 and then down to 3. Those are our useful ranges here. And all of that is sent into the body. So even though we're calling it a 5 megahertz transducer, F0, the fundamental frequency, is 5 megahertz. We're actually sending in 3, 5, 7, maybe 9, maybe 1, but we're sending all of that in. And we're receiving, in effect, all of that back. And the transducer just says, yeah, give it all to me. I'll take 3, 5, and 7, and we'll make a picture out of it. So the echoes come back with multiple frequencies, but the transducer, you know, he's pretty cool. He's like, yeah, fine, give it all to me. I'm fine with that. Well, with dynamic frequency tuning, the transducer, not so much the transducer, this is back in the receiver. The receiver says, okay, I recognize these voltages, which used to be sound echoes, right? But they were converted into a voltage by the piezoelectric element. It goes back to the the receiver. The voltages are at 3 megahertz and 5 megahertz and 7 megahertz. And so that it can recognize, oh, okay, yeah, I see what's going on. We had, you know, there must have been different frequencies going in. That's why I'm getting different frequencies going out. Dynamic frequency tuning could say, well, I'm going to create a picture out of the 3. And then I'll create another picture out of 5, which is what I'm supposed to be doing in the first place. And I'll create a third picture out of the 7. And I'm going to make these pictures, at least in the background, electronically speaking, I'm going to make these 3 separate. And then I'm going to add them all together to create one image. No. Now, why would we bother with this? We're already using, without dynamic frequency tuning, we're already using 3, 5, and 7. We're just kind of mixing them all together and calling it a day. But now we're separating them out, processing them separately, creating little imaginary pictures separately, and then bam, putting them all back together and creating the actual picture with 3 separate sets of data. Well, the nice thing about this is that 3 megahertz has a slightly different noise pattern. When I say noise now, I should say, let's say a speckle pattern. 3 has a slightly different speckle pattern than 5, which has a different speckle pattern than 7. And so now when we process these 3 frequencies separately and then put them together, the machine's able to say, oh, you know, I don't know how to draw it, but it's saying, oh, okay, here's what 3, 5, and 7 agree on, but then here's what these three frequencies don't agree on, and what they don't agree on is rejected. And so by being able to do that, you're able to reduce noise, you're able to reduce some speckles. So let's see, we call it wide bandwidth, broadband, or broadband. Okay. I thought I just described the wrong thing for the wrong name. I didn't, but I did forget half the information. So I'm really glad I looked back at my book here and realized that something was amiss. Hartford and superficial. Yeah. That's, what was it? There was something else I was thinking of. Okay, well, we'll get to it when we get to it. So I almost forgot the actual, probably the more important part of dynamic frequency tuning. Hold on, guys. I'm sorry. As a system is superficial in the image because higher frequency, lower frequency is a deeper portion. Example. Okay. So what I just wrote is, okay, I have this sickening feeling that I did mess something up, but okay. And that's why I have this over here as well. What time is it? Well, it's 11:37. Well, let me finish. Oh shit, no, I wanted to finish 14 entirely. Oh, this is it. Okay. Well, this is plus Alara and output power, and we'll talk about that real quickly too. So I have I'm sorry, guys, all messed up. I have my 3, 5, and 7 megahertz. With dynamic frequency tuning, we could also say that the best imaging in this region is probably going to occur from the 7 megahertz portion of this beam, of this pulse of sound. And then 7 megahertz might not be so good down here. I'm going to overlap a little bit too. I mean, technically speaking, 7 megahertz is always better except for attenuation. So due to attenuation effects, we might be best using 5 megahertz there. And then 5 is always better than 3 unless you're going really deep into the body. And so at that point, because of attenuation, three megahertz. So wait a minute, Kurt, what does that mean? You're putting in, no, it's one pulse. But remember, depth and time are the same thing. If this is 26 microseconds, let's say right at that depth, and, oh, I don't know, let's just double that. Let's say about 50 microseconds at that depth and 100 microseconds at this depth. What the machine can also do is preferentially process from 0 to, I don't know, 30 microseconds. It's going to preferentially process the 7 megahertz because it's already it knows that 7 megahertz is going to do just fine to that depth, to the depth of 30 microseconds, which is of course time, but time and depth are the same. And then after 30 and up to, I don't know, 60, it's going to preferentially say, I'm going to process the 5 megahertz signal because that should be the best signal at that time period of echo receiving. And then from what I say, from 60 to 130 or whatever, I'm going to preferentially going to listen to the 3 megahertz because that's going to be the best. Those echoes are going to be best from the deep end of the system. Yeah. Okay. Just one real quick subject and we're done for the day. Power versus gain. So he writes some of the questions for the SPI. From what I understand, he really likes asking these questions. So let's just go through page 235. 2 sonographer controlled settings, power and gain, modify the brightness of the image. Power, it's just more power, stronger echoes, improves the signal to noise ratio. Gain, also called amplification, alters the strength of the voltages in the receiver, which is, so if you turn up your gain, you turn up your brightness. So actually, let's see, I'm just going to write the word brightness. If I turn up my power, I turn up my brightness. Simply because everything is stronger. But if I turn up my gain, things aren't stronger, but I'm listening harder. So that also will bring up my brightness. And as you could imagine, if I put down arrows, it'd be down arrows all the way across. Increasing my power gets a better signal to noise ratio. Increasing my gain doesn't do anything for my signal to noise ratio. Crappy picture, dark, crappy picture, turn it up, it's still crappy. It's not going to change. But patient exposure is going to be different between the two. So you guys know ALARA, as low as reasonably achievable. And that's what we're always supposed to be following. Doctors, nurses, technologists, we're all supposed to follow ALARA. We want to do as little harm as possible while we're trying to help people, of course. If the image is too dark, first increase the receiver gain, which does not increase patient exposure. That's important. That's kind of like an SPI question. If it's too dark, if he gives you an image that's too dark, what's the first thing you do? Gain. If the image is too bright, decrease the output power. Well, wait a minute. Why would he say that? Honestly, I haven't been teaching you to do that. So this is the part you really have to pay attention to. If it's too bright, he wants you, if he wants the brightness to go down, he doesn't want you to turn down your gain. He wants you to turn down your power. Why? ALARA. Makes sense? Because by turning down your power, you're doing the same thing mostly on your screen. You're just simply darkening your screen. So that's what he wants you to do first in order to save the world. Okay. I'll update you guys on something. I feel like I might have pulled another concept in to dynamic frequency tuning with this example. This is a real example. Compound. Dynamic compound. Okay. Wait. So I might have screwed that part up. I think like I said, I think I pulled in another concept accidentally, but this part here is definitely, and hopefully this made sense. The reason why the machine would choose 7, then 5, then 3, basically because of attenuation. So, okay, let me stop recording here.